You've clicked the right video. The battle between quantum physics and general relativity is one of the biggest mysteries in science, and today we're exploring whether a unified theory can finally bridge the gap. Two of the most powerful theories in physics completely contradict each other. One explains the universe on the smallest scales, the other on the largest, yet they refuse to work together. What if there was a single theory that could unify them? Why do quantum physics and general relativity clash? What makes gravity so different from the other forces? If a unified theory exists, what does it mean for our understanding of space, time, and reality itself? Look up at the night sky. What do you see? A sea of twinkling stars, distant galaxies, the vastness of space. This is the universe we live in, a place of incredible beauty and wonder. But beneath its surface lies a deeper mystery, a cosmic dance governed by laws we are only beginning to understand. These laws dictate the movement of planets, the birth of stars, and the very fabric of reality itself. For centuries, scientists have strived to unravel these mysteries, seeking the fundamental principles that govern our universe. This quest has led us to two of the most successful and yet perplexing theories in all of science: quantum mechanics and general relativity. One describes the strange and counterintuitive world of the very small, where particles can be in multiple places at once, and reality itself is a matter of probability. The other paints a picture of the universe on the grandest scales, where gravity warps the fabric of space-time, shaping galaxies and dictating the fate of stars. These two theories, quantum mechanics and general relativity, stand as pillars of modern physics. They were developed by brilliant minds wrestling with the most fundamental questions about the universe. Albert Einstein, a name synonymous with genius, gifted us with general relativity. This theory revolutionized our understanding of gravity, showing us it wasn't just a force, but a curvature in the very fabric of space-time. Then came quantum mechanics, pioneered by giants like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger. This theory delved into the bizarre world of atoms and subatomic particles. Here the rules of classical physics break down, replaced by a reality governed by uncertainty and probability. These two theories, each powerful in its own right, have led to incredible advancements in our understanding of the universe. General relativity has given us black holes, gravitational waves, and a deeper understanding of the evolution of the cosmos. Quantum mechanics underpins our modern technology, from lasers and transistors to computers and smartphones. Yet for all their successes, these two theories are fundamentally at odds. They present us with a universe divided. Like two pieces of a puzzle that refuse to fit, they offer conflicting descriptions of reality. This incompatibility has plagued physics for over a century, a thorn in the side of our quest for a unified understanding of the cosmos. The problem arises at the meeting point of the very large and the very small. When we attempt to describe the universe at its most extreme scales, such as the singularity at the heart of a black hole or the very moment of the Big Bang, both theories seem to break down. The equations of general relativity, which work so well on cosmic scales, crumble when applied to the quantum realm. And quantum mechanics, with its probabilistic nature, struggles to accommodate the smooth, deterministic fabric of space-time described by Einstein's theory. This clash of titans, this fundamental incompatibility, has been a source of frustration and inspiration for generations of physicists. But the story doesn't end there. Driven by curiosity, scientists pursue the dream of unification, seeking a theory to explain the universe at all scales, from subatomic particles to galaxy superclusters. This quest has sparked exciting research in modern physics. Physicists seek a bridge between quantum mechanics and relativity, exploring concepts like string theory and hidden dimensions. Now there's a buzz of a major breakthrough, potentially revolutionizing our understanding of the universe. To understand the excitement around this potential breakthrough, we need to rewind the clock, journey back to a time before quantum mechanics or general relativity. Imagine a universe governed by the elegant laws of Isaac Newton. This was a universe of order, predictability, a giant clockwork mechanism ticking along with perfect precision. Newton's laws of motion and gravity explained the world around us with astonishing accuracy. Planets traced predictable paths through the heavens. Apples fell from trees with a satisfying thump, their descent governed by the same force that held the moon in orbit. This was a universe that made sense, a universe where cause and effect reigned supreme. For centuries, Newton's laws stood as the bedrock of physics, unshaken and unchallenged. They allowed us to predict the motions of celestial objects, build towering structures, and even launch rockets into space. But as our scientific tools became more sophisticated, cracks began to appear in this seemingly perfect edifice. Enter Albert Einstein, a young patent clerk, with a mind that dared to question the very fabric of reality. Einstein wasn't satisfied with simply accepting Newton's laws at face value. He possessed an unquenchable thirst to understand the true nature of gravity, a force that had puzzled scientists for centuries. His relentless pursuit of knowledge led him to develop his theory of general relativity, a revolutionary framework that would forever change our understanding of the cosmos. Einstein's genius was to realize that gravity wasn't simply a force acting at a distance as Newton had proposed. Instead, he envisioned gravity as a curvature in the very fabric of space-time. Imagine space-time as a giant trampoline. A massive object like a star creates a dip in this trampoline, a curvature in space-time. Other objects, like planets, then move along the curves created by this distortion, much like marbles rolling around a bowling ball placed in the center of the trampoline. While Einstein was revolutionizing our understanding of gravity, a different revolution was brewing in the world of the very small. Scientists delving into the atom, the fundamental building block of matter, were uncovering a reality far stranger than anything they could have imagined. This was the quantum realm, a place where the rules of classical physics no longer applied. Here, particles like electrons behaved like waves, smeared out across space, their properties existing as probabilities rather than certainties. The act of observation seemed to influence the very nature of reality, collapsing these waves of probability into a definite state. This was the unsettling message of quantum mechanics. Concepts like superposition, where a particle could exist in multiple states at once, and entanglement, where two particles became linked, sharing a fate regardless of distance, challenged our very notions of cause and effect, of locality and reality itself. The quantum world was a place of inherent uncertainty, a stark contrast to the deterministic clockwork universe of Newton. As physicists delved deeper into the quantum realm, they developed a more complete and elegant framework to describe its bizarre nature: quantum field theory. This theory went beyond the idea of individual particles, proposing instead that the universe was filled with fundamental fields like the electromagnetic field. Particles in this view were simply excitations or ripples in these underlying fields. Imagine the surface of a pond. A pebble dropped into the pond creates ripples that spread outward. In quantum field theory, particles are like those ripples, disturbances in the underlying fields that permeate all of space. This elegant framework allowed physicists to explain the interactions of particles with incredible precision, unifying three of the fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force. Quantum field theory became the language of particle physics, leading to remarkable discoveries and technological advancements. So we have these two incredibly successful theories: general relativity, describing the universe on the grandest scales of stars and galaxies, and quantum mechanics, governing the bizarre world of atoms and subatomic particles. Both have been tested and confirmed to astonishing accuracy within their respective domains. Yet when we try to combine them, to create a single theory that can describe the universe at all scales, we run into a fundamental incompatibility. Like two languages with no common ground, they seem to speak different tongues, their equations clashing in a cacophony of mathematical contradictions. The heart of the problem lies in the way these theories treat space-time. General relativity views space-time as a smooth, continuous fabric, warped and curved by the presence of mass and energy. Quantum mechanics, on the other hand, suggests that at the smallest scales, space-time itself might be granular, a seething foam of quantum fluctuations. Black holes and the Big Bang highlight the clash between general relativity and quantum mechanics. Black holes test general relativity's limits. The Big Bang demands quantum mechanics. Both theories break down in these extreme environments. The incompatibility of general relativity and quantum mechanics has driven physicists to seek a unified theory. This quest has led to some of the most exciting research in modern physics. From string theory to loop quantum gravity, possibilities are vast. Recent breakthroughs offer tantalizing hints about quantum gravity. We might be on the cusp of a revolution in physics. The search for a unified theory of physics has captivated physicists for generations. It aims to uncover the fundamental principles that govern the cosmos at all scales. Imagine a single framework explaining quarks, electrons, and planets. This grand vision drives the search for a theory of everything. One of the most intriguing concepts to emerge from the quest to unify general relativity and quantum mechanics is the idea of quantum foam. At the smallest scales imaginable, far smaller than even the tiniest subatomic particles, space-time itself may not be the smooth, continuous fabric that Einstein envisioned. Instead, according to quantum mechanics, space-time at the Planck scale, a realm ruled by quantum uncertainty, might be a turbulent, frothing sea of quantum fluctuations, a constantly shifting landscape of virtual particles popping in and out of existence. Imagine the surface of a calm lake on a windless day. Now imagine zooming in on that surface with an incredibly powerful microscope, magnifying it trillions upon trillions of times. At this level of detail, the once smooth surface would be revealed as a chaotic dance of molecules, constantly jostling and colliding. This, in essence, is the picture of quantum foam. Another major challenge in unifying general relativity and quantum mechanics is the so-called problem of time. In our everyday experience, time flows uniformly, a constant backdrop to our lives. We mark its passage with clocks and calendars, measuring the intervals between events with remarkable precision. General relativity, however, paints a different picture of time, one in which it is not absolute but relative, dependent on the observer's motion and the strength of the gravitational field. Time slows down in stronger gravitational fields, a phenomenon known as gravitational time dilation. Quantum mechanics, on the other hand, treats time as an external parameter, a background against which quantum events unfold. This fundamental difference in how the two theories treat time has been a major stumbling block in attempts to unify them. Black holes, those enigmatic objects predicted by Einstein's theory of general relativity, have provided fertile ground for exploring the intersection of gravity and quantum mechanics. They are regions of space-time where gravity is so strong that nothing, not even light, can escape once it crosses the event horizon, the point of no return. One of the most perplexing puzzles associated with black holes is the information paradox. Quantum mechanics dictates that information about a quantum system, such as the state of an atom, cannot be destroyed. This principle, known as unitarity, is fundamental to our understanding of quantum mechanics. However, if a black hole swallows everything that falls into it, including information, it seems to violate this fundamental principle. This paradox has sparked decades of debate and has led physicists to propose radical new ideas about the nature of black holes and the fundamental laws of physics. The hierarchy problem is another major puzzle that highlights the disconnect between general relativity and quantum mechanics. Of the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, gravity is by far the weakest. This vast difference in strength poses a significant challenge for physicists trying to unify these forces. In the framework of quantum field theory, the strength of a force is related to the mass of the particles that mediate it. For example, the electromagnetic force is mediated by photons, which are massless particles. However, there is no known particle that mediates the force of gravity. If such a particle, a hypothetical graviton, exists, it is predicted to be massless as well. This poses a problem because if gravitons are massless, gravity should be much stronger than it is observed to be. Testing the predictions of theories that attempt to unify general relativity and quantum mechanics, such as string theory and loop quantum gravity, poses significant experimental challenges. These theories typically involve energy scales and distances far beyond the reach of current experimental capabilities. For example, to directly probe the Planck scale, where the effects of quantum gravity are expected to be significant, we would need a particle accelerator the size of the Milky Way galaxy. While such an endeavor is clearly beyond our technological reach, physicists are pursuing creative approaches to indirectly test these theories. These include searching for subtle quantum gravitational effects in astrophysical observations, such as the cosmic microwave background radiation, and developing ultra-sensitive detectors capable of measuring minute fluctuations in space-time. Despite the formidable challenges, the quest for a unified theory of physics continues unabated. New theoretical frameworks are being developed, and exciting experimental results are providing tantalizing clues about the nature of quantum gravity. One promising avenue of research is the study of holographic duality. This remarkable idea, which has emerged from string theory, suggests that the universe may be a kind of hologram, where information about a higher dimensional space is encoded on a lower dimensional boundary. Another exciting area of research is the exploration of modified theories of gravity that attempt to reconcile the observed acceleration of the universe's expansion with our understanding of gravity. These modified gravity theories, which often go beyond Einstein's general relativity, could potentially provide a framework for understanding both the large-scale structure of the universe and the behavior of gravity at the quantum level. In the heart of quantum mechanics lies a phenomenon so bizarre, so counterintuitive, that it once baffled even Einstein himself: quantum entanglement. This strange connection between particles separated by vast distances has emerged as a key player in the quest to bridge the gap between the quantum realm and the world of gravity. Imagine two particles born together in a quantum event. They are linked, entangled, in a way that defies our classical intuition. Measure the spin of one particle, and instantly you know the spin of the other, no matter how far apart they may be. Einstein famously called this spooky action at a distance, but countless experiments have confirmed its reality. Entanglement is not just a theoretical curiosity, it's a fundamental feature of the quantum world, and it's now playing a starring role in our efforts to understand the quantum nature of gravity. Black holes, those cosmic gluttons that consume everything in their path, might seem like unlikely places to search for clues about the quantum nature of gravity. But these enigmatic objects hold a secret, a deep connection to thermodynamics, the study of heat and its relation to other forms of energy. In the 1970s, Stephen Hawking made a groundbreaking discovery. Black holes are not entirely black after all. Due to quantum effects near the event horizon, they emit a faint thermal radiation now known as Hawking radiation. This discovery sent shockwaves through the physics community. It suggested that black holes have a temperature and, even more surprisingly, an entropy, a measure of their internal disorder. This connection between gravity, quantum mechanics, and thermodynamics has opened up entirely new avenues for exploring the quantum nature of gravity. Imagine space-time not as a smooth, continuous fabric, as Einstein envisioned, but as a tapestry woven from tiny, indivisible threads. This is the essence of loop quantum gravity, one of the leading contenders for a quantum theory of gravity. In this theory, space-time is not fundamental, but emerges from the collective behavior of these quantum threads, called loops. Just as the atoms in a solid give rise to its macroscopic properties, these loops at the Planck scale weave together to form the fabric of space-time as we experience it. Loop quantum gravity has made remarkable progress in addressing some of the key challenges in unifying general relativity and quantum mechanics. It provides a natural explanation for the Big Bang singularity, suggesting that our universe emerged from a quantum bounce rather than a point of infinite density. In the realm of theoretical physics, string theory stands as a bold and ambitious attempt to unify all the fundamental forces of nature, including gravity. It proposes that the universe is not made up of point-like particles, but of tiny, one-dimensional objects called strings. Just as a violin string can vibrate at different frequencies, producing a variety of musical notes, strings in string theory vibrate in different modes, giving rise to the different particles we observe in nature. These vibrations, however, don't just occur in the three spatial dimensions we experience. String theory requires extra spatial dimensions, curled up at incredibly small scales. While string theory holds the promise of a unified theory of everything, it has also been met with skepticism due to its lack of experimental verification. The energy scales required to directly probe the string scale are far beyond the reach of current technology. Imagine watching a three-dimensional movie. The illusion of depth and realism emerges from a two-dimensional screen, where all the information about the three-dimensional world is encoded. The holographic principle, a mind-bending idea that has emerged from string theory and black hole physics, suggests that our universe might operate in a similar way. This principle proposes that the information content of a region of space is not proportional to its volume, as we might intuitively expect, but to its surface area. In other words, the universe could be like a vast hologram, where all the information about its three-dimensional interior is encoded on a distant two-dimensional boundary. The holographic principle has profound implications for our understanding of the nature of space, time, and information. It suggests that our everyday experience of a three-dimensional world might be an illusion, a projection of information encoded on a distant surface. While directly probing the Planck scale remains a distant dream, experimental physicists have made remarkable strides in testing the predictions of quantum gravity theories indirectly. By observing the universe with unprecedented precision, they are searching for subtle signatures of quantum gravity imprinted on the cosmos. One of the most promising avenues is the study of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves, predicted by Einstein's general relativity, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Gravitational wave astronomy is still in its infancy, but it holds the potential to reveal the secrets of some of the most extreme environments in the universe, such as black holes and neutron star mergers, where the effects of quantum gravity might be detectable. The quest to unify general relativity and quantum mechanics has been long and arduous, marked by breakthroughs and dead ends. Recent advances provide tantalizing clues about quantum gravity, bridging the gap between the very large and the very small. This is a time of great promise and anticipation, expanding our knowledge at an unprecedented rate. The quest to understand the universe is a testament to human curiosity, a journey far from over. While we stand on the threshold of a new era in physics, the universe continues to hold many mysteries yet to be solved. The search for a unified theory of physics is far from over. The recent breakthroughs, while significant, have also raised new questions and challenges. What is the nature of dark matter and dark energy, the enigmatic substances that make up the vast majority of the universe's mass and energy budget? How did the universe begin, and what is its ultimate fate? These are just a few of the profound questions that continue to drive our quest to understand the cosmos. The journey toward a complete understanding of the universe is an ongoing adventure, one that will likely continue for generations to come. Each new discovery, each theoretical breakthrough brings us closer to unraveling the secrets of the cosmos, but it also reminds us of the vastness of what we still don't know. Imagine gazing up at the night sky, not with wonder and speculation, but with a deep understanding of the universe's grand symphony. That's the promise of a unified theory of physics, a revolution that could transform cosmology, the study of the universe's origin, evolution, and structure. With a unified theory in hand, we could potentially unlock the secrets of the universe's earliest moments, peering beyond the veil of the Big Bang, understanding the conditions that gave rise to space, time, matter, and energy as we know them. No longer would we be confined to speculation. We would have a robust framework to guide our exploration of the cosmos. We could trace the evolution of galaxies with unprecedented precision, unraveling the mysteries of dark matter and dark energy, the invisible forces that shape the cosmic web. We could even begin to explore the possibility of other universes, hidden dimensions beyond our perception and the ultimate fate of our own cosmos. The Big Bang, the event that marked the birth of our universe, has long been a source of both fascination and frustration for physicists. It represents the ultimate frontier of our knowledge, a point in time where our current understanding of physics breaks down. With a unified theory of physics, we could potentially rewind the clock, tracing the evolution of the universe back to its very first moments. We could study the extreme conditions of the early universe where gravity and quantum mechanics were inextricably intertwined. We could finally understand how the fundamental forces of nature were once unified and how they subsequently separated, giving rise to the diversity of particles and interactions we observe today. Unlocking the secrets of the Big Bang would not only deepen our understanding of the universe's history, but could also shed light on the fundamental laws of physics themselves. Black holes, those cosmic enigmas where gravity reigns supreme, have captivated our imaginations for decades. They represent the ultimate testing ground for our understanding of gravity, pushing the limits of both general relativity and quantum mechanics. A unified theory of physics could provide us with the tools to finally crack the code of black holes, peering beyond their event horizons, those points of no return, to unravel the mysteries of their singularities. We could study the fate of matter and information as they fall into a black hole. We could explore the possibility of wormholes, hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes altogether. Black holes, once shrouded in mystery, could become laboratories for probing the deepest laws of physics. The idea of traveling to distant stars and galaxies has long captured the human imagination, but the vast distances between stars, measured in light years, pose a formidable challenge to our current understanding of physics. A unified theory of physics could potentially open up new possibilities for advanced propulsion systems such as warp drives that could circumvent the limitations of conventional rocket technology. Warp drives, a staple of science fiction, would work by distorting space-time itself, creating a bubble around a spacecraft. This bubble would essentially surf on the fabric of space-time, allowing the spacecraft to travel faster than the speed of light without violating any laws of physics. While warp drives remain highly speculative, the possibility of manipulating space-time itself could have profound implications for space exploration. The strange and counterintuitive world of quantum mechanics has already begun to revolutionize our technological landscape. Quantum computers, which exploit the bizarre properties of superposition and entanglement, have the potential to outperform classical computers in certain tasks. A unified theory of physics could further accelerate this quantum revolution, providing a deeper understanding of the quantum realm and enabling the development of even more powerful quantum technologies. Quantum computers could revolutionize fields. These fields include medicine, materials, science, and artificial intelligence. They could accelerate drug discovery, design new materials with unprecedented properties, and develop artificial intelligence systems capable of solving problems currently intractable for classical computers. The quest for a unified theory of physics is not just about finding a single elegant equation to describe the universe. It's about pushing the boundaries of human knowledge, exploring the universe's deepest mysteries, and unlocking possibilities we can only begin to imagine. It would mark a new era in physics, opening up uncharted territories for exploration and discovery. With each new discovery, we peel back another layer of the cosmic onion, revealing a universe even more awe-inspiring and enigmatic than we could have imagined. While the recent breakthroughs in physics have brought us closer than ever to a unified theory, the journey is far from over. The universe is vast and mysterious, and for every question we answer, new ones emerge, pushing the boundaries of our knowledge even further. What is the nature of dark matter and dark energy, the invisible forces that shape the cosmic web? How did the universe begin, and what is its ultimate fate? Are there other universes beyond our own? And if so, what are they like? These are just a few of the grand challenges that will continue to inspire generations of physicists to come. What do you think? Can we ever truly unify quantum physics and general relativity? Drop your thoughts and questions in the comments below. Thank you for joining us on this journey through physics theories. Please like and share the video, and please do not forget to subscribe for more videos.